All right. Welcome back, everyone, for another deep dive. This time, we're tackling a topic that's, well, it's near and dear to any developer working with databases.
Yeah.
How to make sure that your MongoDB storage is running at peak performance.
Absolutely. And we've got some really interesting material to dig into today. We'll be covering a few different strategies for optimizing your MongoDB storage, not just to speed things up, but also to keep those costs down.
Yeah, cost is always a factor, isn't it?
Yep.
We'll be focusing on three main areas that our sources highlight: compression, indexing, and TTL indexes.
Sounds good.
Okay, so let's jump right in with compression. I think most of us are familiar with the basic idea of compression, making those files smaller to save space. But in the context of MongoDB, what are the real benefits?
Well, think about it. When you're dealing with large amounts of data, compressing it can significantly reduce the amount of storage space you need.
Right, that makes sense. So we're talking about saving money on storage costs, right?
Exactly. But it's not just about cost savings. Compression can also improve performance because the database has to read and write less data.
Ah, I see. So it's like a two-for-one deal.
Exactly. Now, MongoDB offers a few different compression algorithms, each with its own strengths and weaknesses. The most common ones are Snappy, Zlib, and ZSTD.
Okay, so break those down for me. What's the difference between these algorithms?
Well, Snappy is known for its speed. It's generally the fastest of the three, and it doesn't use a lot of CPU resources. It's a good choice for situations where performance is a top priority.
Got it. So what does Zlib?
Zlib offers the highest compression ratio, meaning it can squeeze your data down to the smallest possible size.
That sounds great, but there's got to be a catch, right?
Well, the trade-off is that it requires more CPU power to compress and decompress the data, so it's not always the best choice if speed is critical.
Makes sense. And what about ZSTD?
ZSTD is kind of a middle ground between Snappy and Zlib. It offers a good balance between compression ratio and CPU usage.
So kind of a Goldilocks algorithm.
Yeah, I like that analogy. It also gives you more control over the compression level so you can fine-tune it to your specific needs.
Wow, there are a lot of options here. Our sources mentioned a case study where a company was able to shrink its database backups by nearly 50% just by switching to ZSTD compression. That's impressive.
Yeah, it really highlights the potential of compression.
So how do you actually go about choosing the right compression method for your MongoDB setup?
It really depends on your specific needs and priorities. You need to consider factors like the type of data you're storing, your performance requirements, and of course, your budget.
Right. Makes sense.
Yeah.
Okay, let's move on to the next topic, which is indexing.
All right.
I know that indexes are crucial for speeding up queries, but our sources also warn against over-indexing. What's the problem with having too many indexes?
Yeah, that's a good point. Well, every index you create adds overhead to your database. It takes up storage space, and it can also slow down write operations because the database has to update all the indexes every time data changes.
So it's kind of like a double-edged sword.
Precisely. You want enough indexes to keep your queries fast, but not so many that you're bogging down the system.
So what are some strategies for striking that balance?
Well, one effective technique is to use compound indexes. Instead of creating separate indexes for multiple fields, you can combine them into a single index.
Can you give me an example of that?
Sure. Let's say you often query your database for documents based on both the name and age fields. Instead of having two separate indexes, one for name and one for age, you could create a single compound index on both fields. That way, the database only needs to look in one place to find the data.
That makes a lot of sense. And it saves space, right?
Exactly. And it can also speed up those queries that involve both fields. It's like having a shortcut to the data you need.
So besides compound indexes, are there other strategies for optimizing indexing?
There are. You can also use something called partial indexes.
Partial indexes, what are those?
Imagine you have a collection of customer data, but you only frequently query a subset of that data, say, customers who have made a purchase in the last month. With a partial index, you can index only those documents that meet that specific criteria.
Oh, I see. So you're basically telling the database, hey, I only care about indexing these specific documents.
Exactly. It's a great way to reduce the size of your indexes and improve performance for those targeted queries.
Now, there's another type of index mentioned in our sources, sparse indexes. What's the difference between those and partial indexes?
Well, a sparse index only indexes documents that contain the index field. It's really useful for fields that are optional or might not be present in all documents. Let's say you have a field for Twitter handle, but not all your users have one. A sparse index would only index documents where that field actually exists.
That's a clever way to save space. It seems like these different indexing strategies really give you a lot of control over how your database performs.
They do, and they can make a huge difference in both storage space and query speed.
Now, one thing that really caught my attention in the source material was the concept of duplicate indexes. They're described as a silent storage killer, which sounds pretty scary. What exactly are duplicate indexes and why are they so bad?
Well, duplicate indexes are essentially multiple indexes that cover the same fields or a very similar set of fields. It's like having two identical copies of a book on your shelf. It takes up space and doesn't really add any value.
So how do these duplicate indexes even happen? Is it a common mistake?
It can happen. Sometimes it's due to a misunderstanding of how indexes work. Other times, it might be the result of changes to your application over time. You might add an index for a specific query and then later forget about it even when it's no longer needed.
Ah, that makes sense. So how do you even find these duplicate indexes lurking in your database?
Thankfully, MongoDB provides a really helpful command for this.
Yeah?
db.collection.aggregate, index stats.
Okay, that sounds like a mouthful. What does that command do exactly?
It basically gives you a report on all the indexes on your collection, including how much space they're using and how often they're being used.
So you can use that information to identify any indexes that are redundant.
Exactly. It's a really useful tool for keeping your indexes lean and efficient.
Okay, good to know. Any other advice on dealing with duplicate indexes?
Yeah, you want to be careful before just deleting indexes. Make sure you understand why each index was created in the first place. Sometimes an index might seem redundant, but it might be there for a specific reason, like enforcing a uniqueness constraint. So, always double check before you hit delete.
Great advice. It sounds like regular index maintenance is important.
It really is.
All right, let's move on to our final topic for today, TTL indexes.
Okay.
Now, TTL stands for time to live. And this seems like a really cool feature for managing data that, well, has an expiration date. How do these TTL indexes actually work?
It's pretty straightforward. When you create a TTL index on a collection, you specify a field that contains a timestamp. MongoDB then automatically removes any documents where that timestamp has passed a certain expiration date.
So it's like setting a self-destruct timer on your data.
Exactly.
What are some examples of situations where you'd want to use a TTL index?
Oh, there are many. Think about things like session data, log files, or shopping carts that have been abandoned. You don't need to keep that data forever, so why waste storage space on it?
Makes sense. You set it and forget it.
Right. It simplifies data management. No more manual cleanup scripts or complex queries to remove expired data.
Okay, so TTL indexes sound pretty awesome. Are there any downsides to using them?
Like any tool, there are a few things to be aware of. You need to make sure your application logic is in sync with your TTL settings. You don't want to accidentally delete data that your application still needs, but overall, the benefits definitely outweigh the risks.
Great. So to wrap up our deep dive today, we've explored 3 key strategies for optimizing your MongoDB storage: compression, smart indexing, and TTL indexes.
Exactly. And remember, even small adjustments can make a big difference.
Absolutely. And it's an ongoing process, right? As your data grows and your needs evolve, you might need to revisit these strategies and fine-tune your approach.
That's right. It's all about finding that sweet spot where you have the performance you need without breaking the bank.
Well said. All right, folks, that's it for today. Thanks for joining us for another deep dive.
Thanks for having me.
Until next time.
See you later.